Yo, 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 what's up, everybody? This is Gamendorf bringing you another session of Fortnite. Oh, wait, that's my other channel. Actually, no, this is Mr. Love, aka the Math Patriot. And no, I do not have another channel. My class just thought that was hilarious. Say hi, y'all.
Hi, Patriot.
Hi, 9-year-olds that play Fortnite.
No, 9-year-olds don't play Fortnite.
Like and subscribe over on Undefined.
Like and subscribe, or my class will undefine you. I don't think that's nice. Okay. Okay, good news. This is our last lesson for Unit 4. Yes, which means you guys have a... Guys, don't embarrass me in front of my YouTube fans. Okay. We got a test and review coming up pretty quick, so just get ready for that. This is our last assignment for it. And anyway, we're doing isosceles and equilateral triangles. I know that you guys know already what isosceles and equilateral means. You should have gone over that in your middle school math classes. So, let's just jump right into it. First off, an isosceles triangle. Now, an isosceles triangle is a triangle in which you have two sides that are congruent. Those two congruent sides are called legs. The non-congruent side is called the base. Notice I did not say that you locate the base based on what's drawn on bottom of the figure. I said the base is the non-congruent side. Here's what you've got to understand. Things in life have bases, and they don't always sit on their base. I mean, think about just your standard cup, right? Just a standard cup. I drew that really, really bad. I mean, sort of a tapered thing, right? Okay, so let's say you have a cup that's got a wider brim than it does a base. And you pour the water in this direction. Let's say that I take that entire thing. Well, first off, where's the base of this?
On the bottom.
The base is right there at the bottom. Now, what if I decide to lay the thing on its side? Where is the base?
On the bottom.
The base is still there on bottom. What if I take the thing and I flip it upside down? The base is still there. Yes, all the water would spill out, but the base is the thing it was designed to sit on, not the thing resting on bottom. Gravity has nothing to do with it. That's about what it was designed to be. You've got to get used to the idea of an isosceles triangle. It does not matter how I draw the thing, that's the base. The non-congruent side. Okay, I can even draw it upside down. Those two are congruent. That's the base. Okay, you've got to get used to the idea. That's going to come up over and over again with different geometric figures all year long. You've got to learn where your bases are, how to identify them, and no, things do not always sit on their bases. Okay, so base angles are the two angles that are at the base. Okay, so you got a base, make an angle off it, that's your base angle. The third angle, the other one, is the vertex angle. So if I ever speak about the vertex, I'm talking about this point right here. And not only are the legs congruent, but the base angles are also congruent. We'll get to that one more in a second. Any questions about the anatomy of an isosceles triangle? No? All right. Okay, the Isosceles Triangle Theorem. If two sides of a triangle are congruent, then the angles opposite those sides are congruent. So here I've got AC is congruent to CB. I jump across, and that means angle 1 is congruent to angle 2. Basically just giving justification for saying that if I know two sides are congruent, then two angles are also congruent. Then, just like any good theorem, we like to look at its converse. In this case, the converse is also true. If two angles of a triangle are congruent, then the sides opposite them are congruent. So if 1 is congruent to 2, then over here we know DE is congruent to FE. And yes, those two guys can be used as fodder when we're doing proofs. Any questions? Anything like groundbreakingly new here? No, yeah, it's all old stuff, right? Okay. So, name two unmarked congruent angles. What do we got? BCA and angle A. How do you know those two are congruent? Oh yeah, because CB and BA are congruent, therefore the angles or the sides, angles opposite those sides must be congruent. Okay. Two unmarked congruent segments. CB and DB? Yeah. CB is congruent to DB. I had someone earlier in the day argue that CB is marked. Well, what's marked is congruent to BA. We're just saying it's also congruent to CB because of the converse of the isosceles property, the converse of the Isosceles Triangle theorem, saying that these two congruent angles also implies congruent sides. Make sense?
Yes.
Questions? No. All right. All right. Given that BC, segment BC, is congruent to BA, find X. Well, if BC is congruent to BA, what does that tell me? Okay, I'm getting various responses here. There's a couple layers to this. The top layer is that my angles are congruent based on the isosceles. Y'all got it? What's it saying? The isosceles triangle theorem, okay? And then because they're congruent, then we know that 4x plus 5 is equal to 5x minus 10. And I hope that our solving skills are getting better now, because I can jump straight to being x equals 15. If you don't believe me, pause the recording and go solve that for yourself. You're going to do probably 2 or 3 steps and you'll get there. All right, find x. So I know that angle S is congruent to angle T. What does that tell me? Yes, SR congruent to RT by the converse of the isosceles triangle theorem. And then, because those are congruent, those two guys equal each other, leaving me with x equals 13. Yay. Congratulations. We're getting so good at this, maybe we should play Fortnite instead.
Minecraft.
Minecraft? No, Minecraft is so old.
Yeah, but it's also very popular for 9-year-olds that have sweet voices.
All I know is my 4-year-old plays Minecraft. Not well, but he does.
No. It should, like 7-year-old leaders for 9-year-olds. You know what?
Okay, moving on. Example 4. Write a 2-column proof. I know you love seeing that so much when you hear that. Write a 2-column proof. I am hoping, thank you for the assistance, guys. Shush. I'm hoping that you guys are getting better at your proving process by now. Angle 1 is congruent to angle 2. And that is given, hold on, let's get this in here. Angle 1 is congruent to angle 2. All right. What are you seeing? 2 is congruent to 3. How do you know that? Angle 2 is congruent to angle 3. That's the vertical angles. That's an M, I promise. Wait. Hold on. Let's have people have a chance to think and process. Let's do orange this time. And then angle 1 congruent to angle 3 by the transitive property. Wow, y'all getting better at that transitive thing. Just Danny, yeah, I know. Hold on. I now know those are congruent, okay? And so now... Uh-oh, announcement. Yay. Okay, football on a math channel. I think I just blew up the universe. Okay. All right, so now we need to show AB is congruent to BC. Hold on, Noah, what do you got? I said Noah.
I don't know.
Wait, I'm sorry, what?
Noah.
I said Noah like 5 times. Exactly. Noah, what do you got? Okay, I got the converse of the Isosceles Triangle theorem. And what's that going to tell me? At this point, I don't care. Okay, because we got our congruent angles, means the opposite sides are congruent. So A, B is congruent to BC. We got our QED, but apparently we don't know our own names yet. Okay.
I think it should be Joe's turn.
All right. Corollary 4.3, the equilateral triangle. Honestly, I don't like numbered corollaries, but I had to do it. Okay, so 4.3, equilateral triangle corollary. A triangle is equilateral if and only if it is equiangular. Remember, if and only if means I can go both directions on it. It's a biconditional. So, if I have 3 congruent angles, then I also have 3 congruent sides. 3 congruent sides also means 3 congruent angles. So, we'll be using that a little bit here in a minute. Also, another corollary to that is that each angle of an equilateral triangle measures 60 degrees. That one would be rather easy to prove. All you got to do is say if it's equilateral, then it's also equiangular. And then x plus x plus x is 180. They all equal 60. Not that hard to prove. But 4.4 corollary is our 60 degree measure for each angle. Sorry, what? All triangles equal 180, yes. Well, the sums of the interior angles equal 180. Okay. Example 5. Find x. There it is. Okay. That was a dad joke. It does not deserve a clap. Stop. Okay. So, equiangular. How do I know it's equiangular? So, equiangular also implies equilateral. So, 5x equals 6x minus 5. X equals 5. Yay. Math. All right, example 6. Okay, I've got what kind of triangle here?
Equilateral. No,
Okay, on the surface, it's an isosceles triangle with a 60-degree vertex angle. Now, whenever I know that these two guys here are congruent, that means that essentially, I'm not going to use x, I'm just going to use a for my angle measure there. A plus 60 equals 180, which means 2a equals 120, so a equals 60.
That is smart.
They're all 60 degrees. It's equiangular, also implies equilateral. Okay. Why would I what? Because they wanted to force you to do that process. Can you figure out that it is equilateral based on the information given? That's why they put that. Well, okay, so the comment, the comment was that it's obvious that it's equilateral because that's 60, these two are equal. Yes, you're right. You went through an entire logic process in your head that I just wrote down right there. All I'm doing is writing it down so that we have proof for it. Okay, so now that we know it's equilateral, now we can. Wait, did you have another question?
Fine, yeah. So, even though it's the isosceles triangle theorem, can you still do it with any other triangle?
No, it only works when you have the isosceles property. The two sides are congruent. Now, an equilateral triangle is a special case of an isosceles triangle. Because it's an isosceles triangle in which the base is equal to the legs. So all your isosceles properties also apply to equilaterals. But no, it will not work for scaling triangles. Yes, we will get into the whole is-a thing. A square is a rectangle is a trapezoid is a. We'll get into all of that as a lot when we jump into quadrilaterals in about 2 units from now. Yes, sir. Okay, so the question was, how do I know that our two base angles down here, Z and Y, are both 60 and one's not 59, one's 61? The reason is because we have it's marked as isosceles. These two guys, the legs are congruent. Therefore, the ones across from them must be equal by the isosceles triangle theorem. Okay. Now we can actually go on to solving this thing. 3x plus 8 equals 4x minus 4. Subtract that gives me x equals 12. Yes. All right. So what was the question? Okay. It actually would have been negative x equals negative 12, and then we're doing it the other way. And then you divide by negative 1 and get x equals 12. All right. Find x and y. This one's an interesting one, I think. Okay, first off, let's take the legs. I've got df is going to fe. So let's set those equal to each other. 6y plus 3 equals 8y minus 5. Subtract the 6y gives me 2y. Add the 5 gives me 8. Divide by 2 gives me y equals 4. Okay, now, our isosceles triangle theorem tells me that equal sides implies that opposite angles are equal. So if angle E is 4x minus 8, then angle D is also 4x minus 8. What about equals itself? No, all three angles add up to 180. So 4x minus 8 plus 4x minus 8 plus 4x minus 8 equals 180. I could do that. Or I could also use one of my corollaries. I mean, look, if I've got 4x minus 8 on all three of them, does that mean it's equilateral or equiangular?
Yes.
And so for an equiangular triangle, each angle measures
60 degrees.
So 4x minus 8 equals 60. How'd you write that in a proof? I would call 4.4 corollary. Corollary is similar to it's essentially like something that's very closely related to a theorem, so closely related that the proofs are so similar that we just call it a corollary too. Yes, we'll call it just corollary 4.3 and corollary 4.4. And it'll make more sense as we go through it. Well, let's get to a proof where we actually have to use it. Oh, no, that's not 52. We're going to add 8, so that gives me 68. Then divide by 4 gives me x equals 17. Man, you are ahead of me, aren't you?
Yes.
All right. Last proof, and then we're done. And guys, I do need complete full attention on this one because this one's a little bit weird. My other classes have issues. I don't want to go back and retrace 5 different steps because you were not paying attention. All right. Okay, write a 2-column proof. Let's just go ahead and get this guy set up for a 2-column proof. All right, number 1, we know that triangle ABC is equilateral and angle 1 is congruent to angle 2. All right, let me go ahead and mark those in. Equilateral. Now, I also know that AC is congruent to AB and BD. I also know that angle 1 is congruent to angle 2. Now, it's asking me, and I put this in pink so we don't get them mixed up, it's asking me to show that ADB is congruent to CDB. So, actually, let me offset that a little bit so it doesn't look like it's the same angle. So just overall, what's the word? Game plan here. I'm thinking that if I could prove that these two triangles are congruent to each other, then I could use CPCTC to show that angle ADB is congruent to CDB. But that means I've got to figure out how to make those two triangles congruent. What you got, Connor? All right, so we got angle A congruent to angle C. How do you know that? Ooh, yes, I like it. Yes. Well, actually, you know what? Technically, all right. Technically, Isosceles Triangle Theorem doesn't directly work here because we haven't actually called it isosceles. We have to use a definition of isosceles to say it's isosceles and do that. I would actually prefer to use definition of equilateral triangle. Hold on. That's a different thing. Okay, we're doing this one with angles and something. All right. So for our congruent. Oh wait. We said angle. Oh wait. Actually, you know what? I read that completely wrong. Hold on. I'm gonna told Connor something wrong. Angle A is congruent to angle C. I was thinking side lengths that entire time. Yeah, angle A congruent to angle C. So let's look back. What do we have that says an equilateral triangle angles are equal as well? Is that's corollary 4.4? Each angle measures 60 degrees. We've also got corollary 4.3 is equilateral if and only if it's equiangular. That's the one we actually need to use. Okay? It is corollary 4.3. That is going to be equilateral corollary 4.3. And that should be a 2 there, not a 3. Okay, so. Yes.
So, like, say 1 and 2 are both 3.
Actually, you know what? That's a route I didn't think of. Because the route I was thinking when we talk about the game plan is proving the triangles are congruent and doing CPCTC. But okay, so the bisector, yes, it is a bisector, but it's not as important. However, since I know that angle A and angle 1 are congruent, A is congruent to C, 1 is congruent to 2, I can use the third angles theorem to show that the third angles are congruent. So that's actually faster than I did it earlier in the day. I don't think that's exactly what you meant. But, I mean, what you were essentially saying was that since these are equal and those are equal, we could then know that these guys are.
No,
You were trying to go by the bisector?
No, I was saying that since angle 1 is congruent to another unit, that
Okay. So, next unit, we'll get into the properties of isosceles triangles and their bisectors and medians and altitudes and all that sort of stuff. As of right now, we can't do that. We will have one that says that exact property, but we got to wait like 2 weeks to get there. Okay? So good observation. We'll come back to it. Okay. So now I want to go the longer route I originally thought, or we want to go the shorter route? Okay. All right. So scrap what I said about CPCTC. Let's use the third angles theorem. Third angles theorem, and that is going to say that angle ADB is congruent to angle CDB, and now we are done. Not too bad, right? Okay, so that's it for our lesson. I'm going to go ahead and sign off. This is Mr. Love, aka the Math Patriot. Don't play Fortnite, it'll rot your brain. Don't play Minecraft, it'll rot your brain. And my 4-year-old will make you look even worse because of his awesome stuff. And as always, stay patriotic.